Okay, let's start. Uh, so today we are actually, the main topic is about counting. We are going back to real life. Last time we were talking about infinity, so it's far away from real life. And but that is the last time we are going to be away from life. In the remaining of the semester, we will come back to life, to Earth. So in the set theory part, in the infinity part, so I left out a theorem, which is a very important theorem in set theory. I skipped the proof because I want to say that I want to start where everyone's mind is fresh. Okay, so hopefully now we are very energetic. Our minds are fresh. Okay, so first let me read the theorem, what we want to show. Okay, so the theorem says this. For any set X, you give me a set, like a very abstract set X. Let's consider its power set. So let capital Y be the power set of X. That is, the capital Y collects all the subsets of X. Right? So Y consists of all the set S, where S is a subset of the given set X. Okay. Now, the conclusion is the Y has strictly larger size than X. Okay. So we'll see this. We'll spend 20 minutes on this. Okay. But what is the significance? So the significance of counter theorem says there is no set with the largest size. So in other words, infinity, in the world of infinity, we can keep on going, right? So no matter how big the infinity we have seen, there's always some bigger infinity, right? Because take any infinity X, just look at its power set of X. Then it is a larger infinity. So the world of infinity goes on and on and on, never finish. Right? So this is a how to say? This is significant, right? So you can keep going along the stairs of infinity. Actually, counter named these cardinal numbers, Aleph 0, Aleph 1, and so on and so forth. And then he probably called this the stairs to God or something. So he was thinking the pure infinity is somewhere like only God knows. Anyway, so the significance of counter theorem is there's no largest infinity. Okay, so now we want to prove this. So now let's. This is really mathematics. Okay. So please, how to say? Stay with me for another 20 minutes. Okay. So I want to. Okay. So let me first read the 6 lines, and then I'm going to use the blank page to draw some pictures to explain the 6 lines. And then probably after that, I hope the 6 lines makes more sense. Okay, so let's first go through this. Okay, I want to show the Y is strictly larger than X, right? So first, let's show Y is at least as large as X, right? That's the easy part. Okay, so in other words, we want to see Y has at least as many elements as in X. So the mathematical way of doing this is to define an injection from X to Y, from X into Y. So therefore, inside Y, you have a copy of X. So therefore, y should have at least as many elements as x. So the copy of x is very easy because take any element, small x from capital X, you can form a subset only contains x itself, right? Now define, so you map the small x to we call it singleton. We call it a set which contains a single element x. This singleton x. Now this function f is clearly 1-to-1 because right, if x1 is not x2, the set of x1 is not the set of x2. So this clearly 1-to-1, and then that demonstrates y has at least as many elements as x. Right. So this is an easy part. Now this is the complicated part. So we want to show they cannot have the same size. But those sets are so abstract. Is how can we show, right? So you can. I'll convince you that there are some kind of diagonal argument inside. There are some clever diagonal argument. So let me read it. Let us read this together for this moment, and then we do it in slow motion, draw pictures, and explain what's going on, and then we come back again. Okay? Okay. So let's try. Let's just read it. If you don't understand it, fine. So this is a complicated proof. So we want to show this. We want to show any function f from x to y is not onto. In other words, any attempt to match x with y must miss something. Remember last time we have seen an example. We showed natural numbers are strictly less than decimal points between 0 and 1. Right? So the proof there is no matter how hard we try, there are some elements we miss. Right? So here we want to use the same idea. So suppose you have an attempt, which is this function f. Try to match the elements between x and y. Right? So we want to show that it cannot be onto. In other words, there will be some point you miss. You cannot hit every target. There must be something you miss. Okay? So now that takes one line. The remaining 4 lines will say which element you miss. Okay? So this is an element you miss. Consider this set. Okay? This set S collects all the elements small x such that the small x is not in the image of f of x. This looks extremely abstract. But you can see it has a flavor of the diagonal argument or the Russell's paradox. So I collect the element which is not belong to something, the something related to myself. Right? So I want to do, I collect element which, if the element doesn't belong to somewhere, I collect it. If the element belongs to somewhere, I will reject it. So it's kind of like the Barber's paradox. We are trying to create a situation like that. We'll see some details in a moment. Okay, so let's just see this, right? So we consider this set X, this set S. The S will be the set you miss, the function f miss, right? So this is a set. Okay, I don't really. Okay, so now we claim that S is not in the range of f. The capital S is the set you miss. Okay, so how do we show that? This is a very small proof by contradiction. So suppose you don't miss it. Suppose it was hit. This S was hit by f. So there will be some element z from the domain, from capital X, so that f of z is the set S. Right? This is, suppose it is in the range. You hit it. There will be a z from the domain, so that f of z is the target. Okay? So fz is S. Okay, here, comes contradiction. So then let's look at the Z itself. Right? Every element, okay. So let's look at Z itself. Is Z belong to S or not? Okay. So if Z is in S, then by definition, okay, any element in S will have this property. He is not in the F of himself, right? So now Z is in here. So Z must have this property. So Z cannot be, well, there are several, okay. So Z, let me follow my train of thought first, which is the same as this. Okay. So Z is in S. So the okay, let me follow my train of thought first, and then which is equivalent to this. Okay, so if you look at Z in S, if you look at the definition of S, you'll get Z is not in F of Z. Z is not in F of Z. But on the other hand, by the choice of this Z, what is the Z? Z is exactly Fz is S. So Z in S implies Z is in Fz. Then you get a contradiction. Right? So that's the whole argument. It's so strange and okay. Now let's do it again in much more detail with lots of examples. Okay. Yeah, abstract examples. I cannot give you concrete examples. Okay. So let me try. So here is the okay, so first let's look at an example about power set. Okay, so let's look at a simple example. Let us look at a finite example. Example of finite sets. An example. Okay, so let's say X is just ABC. It has 3 elements. Okay, so let's do this. Okay, so what is the power set of X? We have done it before, I know, but let's do it one more time. So it collects all the subsets of capital X. So it first collects empty set. The subset has no elements. Okay, and then it collects subset of X, which has exactly 1 element. So for that, you can collect this singleton A, right? The element, the set which has only 1 element, which is the A, right? So this is the singleton A is a subset of X because right, every element in singleton A is A, so it's also in X. Okay. And then you have singleton B, and then you have singleton C, right? So the set of A, set of B, set of C, they are subsets of capital X. So power set should collect them. Okay? So then these are the 1 element subset of X. Okay. So now let's take 2 elements subsets. Okay. So then you will get A comma B. So this is a subset of X which has 2 elements, right? And then you can get BC. It's another 2 element subset. And then you have CA or AC. No more. These are all combinations because there's only 3 elements, so it's very easy. So that exhausts all the 2 element subsets. Now there's one more set, which is the 3 element subset, which is X itself, ABC. Right? So we exhaust the element of 1 element. The set of 1 element consists of 1 element, 2 elements, 3 elements. Do we have more? No, because X itself only has 3 elements. The subset cannot have more. Right? So that's the the end of the power set. So the power set has 8 elements, right? So now if you look at the size, the size of X is 3, ABC is 3. But if you look at the power set of X, we get 8 elements. So this is 8, and this is 2 to the power of 3. Later, we are going to do counting. We are going to show something called binomial theorem. And this is not a coincidence. This is actually true. So the power set, why we call it power set, it related to power, to the computational power. Okay. So this is an example. And from this example, certainly we have, even for finite set, the size of X is strictly less than the size of power set X, right? In this particular case, right? And also, I'll say that, but I don't want to write on this. Also, in the 6-line proof, you'll see that I define an injection from X to power set of X by sending A to the singleton set A, B to the singleton set B, C to the singleton set C. So I'm saying inside the power set, there's a copy, almost like a copy of X. The copy is this, right? Because you have A, I have the singleton A. You have B, I have singleton B. If I have C, I have singleton C. So I have a subset which match here. So therefore, this logic applies to any set, not only for 3 elements. You can imagine for any elements you have A, B, C, D, E, F, G. I would have bracket A, bracket B, bracket C, bracket G. Right? So this embedding is easy. So this is an example which we can have a little bit more feeling. Okay. Okay. So this is the easy part. So now I want to explain the hard part. Okay. So where is the? I don't know how to do. Okay. So good. So now what is the hard part? So now we have, okay, so now given X and its power set Y, which is its power set, I want to do the proof. I want to do the proof on this blank page of paper. Okay, so first I want to draw some pictures so that we know. Okay. So here, the picture cannot be too serious. So, okay, so here I have X. Here, okay, so let me draw it a little bit larger. So I have Y. Okay, so now our goal is to show. Okay, so let's first do it slowly. X is strictly less than Y, right? So, and we already seen. We want to show this. We want to show. So that is any attempt, any f from X to Y is not onto, right? So this is what we actually want to show. I want to show you cannot match the element between X and Y. So give me attempt, right? You say, oh, I can do it. So show me your attempt. So F is the attempt. Attempt F, okay, F is a very clever match from X to Y, right? Maybe you can do something like this. And so that A, by an argument like Hilbert Hotel, there's some very, very smart argument. And somehow you can match the two circles, the two sets. Maybe you can. Okay, so you give me this F. So this is the F you give me. Say, I give you F from X to Y. Okay, so now I must show you. I must show this F. Can I write in a non-mathematical term? This F must miss some point in Y, right? So I want to demonstrate this is not onto. So therefore, I must find some strange element z. And I have to say, look, the z you miss. The f, no matter how clever you do, there will be a blank point, like this z. This is strange, right? All the information is on this paper. Okay, so there's x, there's y, and some clever people draw some line. I have to show you that this z, there's a z. So it's difficult. Okay, so let me continue. I don't know how to. I'm very bad at managing this. Yeah. Okay. Good. Okay, so now to do this, we have to use the property of power set. So there must be something special about power set. Yeah. Okay, so allow me to draw a few more pictures. Okay, look at this x I draw here, this y, a little bit larger y here. Now you have this clever f, potential clever f, right? So now I want to look at the points in y in more closely. So you give me any point here, I don't know, maybe you have an a, so here there's a fa, right? So a will be mapped to somewhere, fa. Now here I want to use the property of power set. So now since fa belong to y, which is the power set of x, actually fa is itself a subset of x, right? Because all the elements in y are subsets of x. So although the fa here I draw as is a point, actually it's a subset. Okay, so let me do this. So let me blow up this point. So fa actually, if you blow up, right? So if you have a copy of x here, this fa actually is a subset of x. So I don't know. So if I draw it on x, like a Venn diagram, fa actually looks like this because it's a subset. So it takes a region. So inside y it is a point. But however, if you look at what's happening in x, it actually take a region, take an area because it's a subset. It collects lots of things in x. Okay. Now let's do one more. Draw one more picture. And okay, let's choose blue. So if you have a b here, you get fb, right? So fb, although it's a point in y, if I blow it up, okay, so I draw another copy of x. So fb, I don't know, fb is maybe it's like this. Okay. So this shaded region is f of b, right? It could be like that. Okay, so here you have f. So f will send elements from x to y. Now what I did is just I use a property of y, because each point in y actually is a region in x. Okay, good. So you're with me, right? Okay, so now I'm going to construct this strange set, which has a flavor of paradox. Okay, so now I define the strange set S. Okay, so S, I define it. What letter do I use? I use small x. So small x in capital X, so that the small x is not in f of x. Okay, I will show you the line on the slides in a moment. So I'm going to define a set like this. So now what is this S from this picture? Okay, so I'm going to collect. So first, this S is a member of the power set because it's a subset. Okay, sorry. S is a subset of capital X because it collects elements from X. So it's a subset of X. So S itself is a member. S will be some point here. Okay? Okay, so S will be some. So now let's look at this picture to see what S collects. Okay, just example pictures. Okay, so now how about this A? Suppose A is like this, FA is like that. Is A in my collection S? Okay, just so in the picture, above. Okay, so I want to know, is A in S? I want to know this. Okay, so let's try. So where's A? A is here. Okay, so A is, okay, so A probably is there, right? Because my black circle is X, and then this red circle, supposedly a duplication of capital X. So A is there, so probably A is somewhere there. Now from this particular picture, A is not inside f of A, because like f of A, I said if you blow up, it takes a region which is a shading. So A is not in f of A in this picture, right? But then A actually qualified to be in my collection S, because I will just collect these guys. The guy who are not in the S will collect those guys which are not in the image of himself. Right? For example, this particular A is not inside FA, and then S will very happily collect this A. Okay. Now, how about this B? I hope I draw a picture somehow. Is B. Well, I draw another picture. Okay, look at this B. I don't know. So B is B in f of B. Well, I don't know. So this B may be here. So B may not. Okay, so in this case, B is B in S. I don't know. Okay, so now in this picture, probably B is not. B is in S, right? Again, because B is here, FB is somewhere on the upper part. So maybe B is down there. So B is not in the image. Then S will happily collect this B. Okay. So now I want to draw a situation where C is inside f of C. So let's draw it together. Okay, so let's try another color, orange. Okay, maybe C is here. C. Okay, so now FC is somewhere. I don't know. Okay, this is FC. Okay, so now in the duplication, this is capital X. Okay, I hope I will draw a shade which contains C. Okay, so maybe C is here, right? So I backward engineering to get FC. So here's FC. If I blow up, maybe take this region. So in this case, the orange C is a member. Of FC. So C, okay. So the capital S will not take C. Right. So suppose if it happens, C is inside the FC, which is the region here, and then S will reject it. Right. S is this diagonal thing. How to say? If you say yes, he will say no. If you are belong to the image, S will reject. If you are not belong to the image, S will take it. Right. So it's doing the opposite of something. Is this okay? So from this picture, I'm going to refresh the paper again, so that now I have defined a set S somewhere. So can I move on? So okay. So now let's duplicate. Let's duplicate this X and this Y. Okay. So now I have subset of, okay, so I have a collection of S somewhere. So I define S to be all the points in capital X such that X is not in f of X, right? And also I have convinced you that S is a subset of capital X, so S actually is a member of power set of X, which is Y. So this area here actually is a point inside Y. Right? Sorry, I defined a diagonal set, the set capital S, which is a subset of X. Last time, in the previous page, I wrote that. So it is a point inside power set because power set is one level more abstract. So S is a. So here I have a region, and then actually it is a dot inside Y. Okay. Okay. So now I have these F. I have the clever function F. I have a clever function F from X to Y, right? So I already have this S. So now the question is, does S belong to the range of F? Right? So I have this point here. This I circle it to highlight this point S. This is a point in Y. Right? I want to show you, I want to demonstrate this point S is not in your range. Right? So I want to so the answer is I will show you that S is not inside the range of F. So your clever function did not hit this point. Okay, so my plan is I'm going to show you this. Okay, so now I can squeeze. Is this okay? So far so good, right? So now maybe I start a new page and write that argument. So we have this set. I'll remind you what set is. Okay, so let's do this proof. Okay, so we have change the color of the pen. Okay, so what do we have? So we have S. We have S, which is defined to be small x in capital X, such that small x is not inside f of X. Right, so we have this. I copied on the set. Okay, so now the claim, the thing I want to convince you is S is not inside the range of F. Okay, so now let's see the proof. So this is a small proof by contradiction. So this is a small proof by contradiction. Okay, so suppose S is inside the range of F. Now the meaning of in the range is you are hit by some arrow, right? So that is there is some Z inside the domain, which is X, such that f of Z is S. This is the meaning of the range. If you are in the range, you are hit by some arrow. So the Z is the person who shoot the arrow, and Fz is the target, right? So we have this. Okay. So now here we get a contradiction. So now look at Z. Look at Z. So Z is in X. So the picture is here. I have x here. So you have z. Right, z is some element here. Now, just now I draw, there is a s. S is a subset. Right, s is a subset of x. So s is this region surrounded by the dotted line, right? Something like this. So z is a point. So I can ask whether z is in the region or not in the region, right? So I'm in the situation, and now I zoom into x. So inside x, I have a dot z. I also have a region, capital S. So I want to see whether z is in S or z is not in S. Okay. There are only two possibilities. Either it's in or not. So if z is in S, okay, z is in S. Okay. What does it mean? Now you have two ways to use S. Okay. One is, okay, S is fz. The other is the double underline. S is the funny diagonal. So I want to use the single underline and double underline, and then create a contradiction. Okay. So now, if I look at a single, okay, so let me label it. I call this one 1, this equation 2. Okay. So the okay, single underline is 2, double underline. So this is 1. So now by 1, by 2, I get, okay, z is in S, right? Z is in S, then S is fz. So z is in f of z. Because, okay, z is in S. S is fz. By replacement, by substitution, z is in fz. Okay. Now, by 1, so z is a member of this set. What are the elements are qualified inside this top set? They are exactly the guys which are not in the image. By 1, z is not in fz. This contradiction. You cannot have he is both in and not in. So this is contradiction. Now, the other case is if z is not in S, it's the same argument. So if z is not in S, then you have the same situation. So let's do it since it's short, right? So by 2, I replace S by fz. So z is not in fz. By 1, he is not in S. So he cannot satisfy the condition in the curly bracket. So z is not the case, z is not a member. So z is the fz. Also a contradiction. So no matter what you do, you are doomed. So therefore, why we are doomed? It's not because it's because the assumption, the set S is in the range. Right? So therefore, there must be something wrong with the assumption. So S is not in the range. So you missed the S. Okay, so it takes 40 minutes almost to explain. But I hope, because this is really, okay, short proof doesn't mean easy to understand. Long proof doesn't mean, some proof are very long, but it's very easy to read. But this proof is very short, but it's very hard to create. It requires some smartness. Okay, so can we go back to the? Let's go back to the. Maybe I just close this. I want to go back to the slides. Okay, so let's look at this. Let's recap this, right? So let me repeat the 5 line. Okay, so what we are so we want to show there's no match. We want to show power set is more than the original set. Okay, so we show any function from x to y is not on. You'll miss something, right? Okay, so now we drop all these pictures. So we straightly go to this funny set. The set was defined in the way like diagonal argument. So we define S to be the small x from the domain, so that small x is not in the image of f. So this is the set. Now we claim this set S is what you missed. It's not in the range. So now these 3 lines are the proof by conclusion. Right? Suppose it is. Suppose for the sake of contradiction, it is in the range. So S is f of z for some z. And then you have trouble. The trouble is no matter if you are in by the argument, you are out. Because this if and only if is double arrow. So if you are out, by tracing back, you are in. So no matter which way you get trouble. So therefore, you always get a contradiction. It means the assumption S equal fz is wrong. So S is not in the range. So you miss S. Okay? So that's the proof. Okay, so I don't know. It's complicated. It's okay. I want to say just one more comment. So we introduce logic, and then somehow we take a look at this world of infinity. So I want to say that mathematics, actually, it is true. Mathematics study lots of abstract things. Because those abstract things doesn't exist in the physical world. Only logic can control them. So you need to know those logic in order to understand mathematics. Right? Because, for example, we want to show there's larger and larger infinity. How do we show? We cannot do physical experiment. We cannot create a large infinity there. Look, this is a larger infinity. So the thing is, we just, in our mind, we just go through these funny arguments, and then suddenly we convinced that there is a larger infinity. And not only is one large infinity, it's larger and larger and larger and larger. It is forever. So it's well, mathematics is different. So I think these illustrate some characteristics of mathematics. All right, so let's take a early break. Then after that, we go down to the real life. We do a finite set counting, and look at cars. And, okay, so let's take a short break. Okay, so let's continue. So now our life is much easier. Okay, so we want to do some counting, which are counting of finite sets. Okay, so the outlines are, first there are some basic principles. We have to use multiplication a lot. And actually, we are going to use factorial a lot, which is a sequence of multiplications. Okay, and then we'll introduce some symbols for permutations and these combinations. These are numbers. And we are going to show binomial theorem, and then there are also examples of counting things from, well, real life or sort of real life. Okay. All right. So I believe that in some JC you probably have seen this more than one time. But anyway, so let's start. Okay. So the motivating example is this poker. I don't play poker, so I don't know. I don't know the names. Okay, if it's because people ask me, do we need to memorize these? I don't know. If you want to play poker, maybe you need to memorize. But if you want to pass the course, you don't need to memorize. Okay. Okay. So they are in poker. So poker is I guess it's a card game, and then there are different patterns, and then somehow if you hit certain pattern, you get lots of money. Okay. So there's some ranking. So this is rank number 1. It's called Royal Flush, right? So it's like the same suit and like this. And then you can have not from ace, king, and so on and so forth. You start from maybe some smaller numbers like 9, 8, 7, 6, 5, and so this is called the straight flush. Okay. So there are patterns of these, and then there's a ranking. Okay, so now we want to know, we want to count how many ways to get certain pattern, right? For example, let's look at this, 3 of a kind. So you have 3 2, or you may have 3 king, or you may have 3 tens. So there are lots of different ways getting 3 of a kind. So now we want to count, right? So we want to count how many ways are there to get these, okay? And also, is there a reason why the casino rank things in this way? Obviously, they are, right? So after you do the counting, you know that this is more rare. This event will be less common than others. So that's why you probably are paid more money if this thing appears. Okay, so we'll learn some counting principle. In the end, we are able to together with tutorial problem, we are going to find out all 10, how to count the 10 sets. Okay, so that's the example we are going to do. Okay, but before that, okay, so let's start from the basics, right? So the basic thing is called the multiplication principle. Let me illustrate by this very, very simple example. So suppose you have 3 heads, A, B, C, whatever, and 2 coats. Maybe in Singapore, coats is not very common, but this is from other textbook, right? So you have two coats, or 2 shirts, whatever. So coats are 1 and 2 in your closet. Okay. So assume you feel comfortable with any combination. Now the question is how many different choices, how many different combinations do you have? Now, okay, let's do it slowly. So for coat, you have 2 choices, right? 1, 2. So we draw it like a tree. So you have, this is choice 1, this is choice 2. Now for each choice of coat, you can choose different heads, right? So for this node, there are further 3 branching here. The same for the choice or the second choice. You also have another further 3 choices. So now how many combinations? If you try the combinations, you should count the leaves of the trees, right? So there are 6, right? So it's 2 times 3. So this is the message I want to say. Because of this example, we understand there's a general principle. So the general principle is called the multiplication principle. So it says this: assume a task which like you dress yourself, Assume a task can be broken up into 2 consecutive steps. If step 1 can be performed in n1 ways, it's like you put on code, there are 2 ways. Right? And step 2 can be performed in n2 ways. It's like put on the head, you have 3 ways. Right? And then the task itself can be performed in, this is multiplication, 2 times 3, 6 ways. Okay, so this is a very easy principle. But we are going to use it over here. Okay, now here is only two steps. Suppose you have m steps, well, just multiply m of them. Okay, so I will not read. Okay, so there's a small caution, like in order to do this, you need to know that there's no restrictions. It's not, so the choice has to be independent. You cannot say, once I choose this code, I must wear this hat. If you have that restriction, then you have to count in a different way. Okay, right? But usually we won't see this. Okay, anyway. Okay, so let's apply it to an example. Okay, so in Singapore, the car lessons, car plates are like this. Okay, so the first letter is always S. Well, and the next 2 positions are so followed by 2 letters from A to Z. Right, so the next 2 positions are held by a Roman letter. Then followed by 4 digits. 1, 2, 3, 4, or 9, 1, 2, 3, or something. And the last one again is a single letter. Okay, so now the question is how many different plates? Okay, so this is the question: how many possible number of plates are there? So the answer is this. Why? Because the first position there's no choice. There's one choice. Now for the second position you have 26 because you have 26 letters, and then for the third position you have another 26. So you'll see the last position also you have 26. So it's 26 times 26, 26 to the power of 3 for the 3. For the second position, third position, and last position. Okay. Now in between there are 4 positions. Each of them has 10 choices because there's 10 digits. So you multiply them, you get 10 to the power of 4, and then multiply everything together. Right? So in other words, imagine that forming a plate number takes 7 steps, right? So there are 1, 2, 3, 4, 5, 6, 7 steps. Each one you have the corresponding number, and you multiply them. Okay, so that's simple. Okay, so now I want to introduce some numbers, some notations. So let's look at this. So the question is, how many ways are there of arranging n things, n distinct objects in a row? So let's think of the n distinct objects like numbers, 1, 2, 3. So the first object is just 1. The second object is 2. Right? So how many ways to arrange n numbers? Okay. So the solution is, again, we think of this task as n steps. Right? To accomplish this task, there are n steps. The first step is to determine the who occupied the first position, and then the second, and so on. Okay, so there are n ways for the first position because, right, you have n numbers, so there's n ways. But after you put your favorite number like 2 to the first position, you don't have 2 anymore, right? So you only have n minus 1 numbers in front of you. So you have n minus 1 maybe choices for the second position. Well, ... Right? So then the last position, you only have 1 number, that's it. Okay? So by the multiplication principle, the total number is this product, n times n minus 1 times ... times 2 times 1. So this is a consecutive product from 1 to n or from n to 1, depending on how you look at it. We are going to see this number a lot. So we introduce a notation called factorial. So this escalation mark is a mathematical symbol. It's factorial. Okay, so it's called a factorial. There's a convention. Okay, I don't think we use 0 factorial too much, but maybe from occasionally we see 0 factorial. If you see that, treat it as 1. There's no reason. Just define that way. Okay. So 3 factorial will be 3 times 2 times 1 is 6, right? So on and so forth. Okay, good. Now let's. This is a subcase of that. Okay, so let's just read it very, very quickly. So in how many ways can you form a row of 3 distinct different objects from 8 different objects? Okay, so I have 3 positions to fill. The first one, I have 8 choices because I have 8 different objects. After I fix the first one, I have 7 choices, right? I have 1 less, so, and then I have 6 choices, so together is this number. Okay, so easy. Okay, so now in general, it's like these. I choose 8 different objects, put them on a row, choose 3, how to say? I have 8 options. I pick 3 of them, arrange them in a row. Right? So now let's use letters. So I have n different objects. It's like 8 here. N is the 8. Then I want to arrange in a row only k of them, only 3 of them. K is the 3 in the example. So how many ways? Well, so the answer is this, is the n factorial divided by n minus k factorial. This looks a bit... okay, if this is the first time you see a factorial, you probably feel very difficult. But it's very easy to see this is n times n minus 1 dot 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 times 3 times 2 times 1, right? So the top. The bottom starts from n minus k, and then n minus k, then you have to minus 1, and dot 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 3, 2, 1. Now the tail will be cancelled. So you cancel everything up to n minus k. So you get here, you get n minus k plus 1. Okay, on top you have bunch of product, but you stop at n minus k plus 1. This is exactly the same as this, right? So this is 8 factorial divided by 8 minus 3 factorial. Right? So 8 factorial is the product of this. 8 minus 3 is 5, so it's 5. Okay, so why don't I only miss 4 numbers, right? It's, 2 numbers, why don't I write it? Okay. Okay, on top you get the product of 8 numbers. On bottom you have product of 5 numbers. Now, if you see that, the tail get cancelled. So actually, what's left is just 8 times 7 times 6. So this formula saying the same thing, but in a different way. Okay, so there are lots of ways of reading this. It's called the k permutations of n, and unfortunately, in the literature, you see lots of different ways of saying the same thing. You can use anyways. It's just there's a p for permutation. Then there are 2 parameters n and k. Then you can arrange it in all sorts of ways. Okay, so now we want to have some more complicated examples, right? If it's all straightforward, then we don't need to learn it. Okay, so let's look at one more example. So now we want to arrange some beads in a row, but the beads has colors. So we have 3 red beads, 4 green and 5 blue. So we want to arrange them in a row, and we want to count how many different ways. So okay, so we do it in a very, very slow way. So suppose these, ignore the colors, right? Suppose they are all different beads. How many ways? Now we know. So altogether we have 3 plus 4 plus 5, which is 12 objects arranged in a line, so it's 12 factorial. But the color give us some problem because there are some double counting, because the three red beads, right? Let's call it R1, R2, R3. They are the same. So if you have R1, R2, R3, and R2, R3, R1, they are the same thing because you can't tell the difference. So therefore, you have this naive way it has lots of overcounting because it assumes they are all different, but they are not. Okay. So now we want to say what we want to do is just get rid of these double counting, right, or the overcounting. So you see the observation is permutation of the beads of the same color will yield the same arrangement. In other words, we overcount 6 times for red because the 3 objects, the 3 red, we imagine they are different, but they are the same. How many different ways of arranging the 3 red? There are 6 ways. So we overcount 6 times, right? So we just divide them. Okay, so the answer is there are 3 factorial ways to permute the red. There are 4 factorial to permute the green, and 5 factorial to permute the blue. So these are the factors of overcounting. Okay. So the total number of ways will be this number. Then we divide them so that we treat them as 1. We treat the 6 ways as 1 way. Right. So if you do this, you are done. Okay. So now this theorem is saying the example in letters. I will not read it. So it's just saying exactly the same thing. Now, okay, so now let's see another example, possible variation. This is a variation of the same theme. You just try to count things. Each time you add some more conditions. Okay, so now we don't do things on the line. Instead, we do it on a circle. Okay, so in how many ways can you arrange 3 guests around a table? Okay. So 3 guests are A, B, C. Okay, so now what's the difference between arranging things on a line and arranging things on a circle? On the line, you have the first position and the last position. On the circle, well, no. So on the circle, these 3 positions, okay, let's imagine that, okay, so this is the most important position. Okay, so A is here, and A, B, C, and okay, C now sitting at the most important position. CAB and BCA, they are on the line is different, but on the circle, actually they are the same, right? Because you can turn them. Okay, so we have overcounted. Right? So if we treat it as if we are on a line. So how many ways of overcounting? So 3, right? Because think of this position held by A. And these 3 things actually are the same. So you overcount 3 times. Okay, so the solution, okay, so let's read it. So if we were arranging them on a line, it would be 3 factorial, right? 3 objects on a line. But we overcounted 3 times because just like the example, ABC, CAB, and BCA, they are the same. So therefore, you have to divide them. If you divide, you get 2. There are 2 ways to arrange 3 people. So in the homework, in the tutorial, you have arranged 10 guests and 9 guests. Or anyway, so you will have lots of exercises. Right? Okay. Alternatively, you can okay. All these counting, there are zillions of solutions. I think people like you, they are so smart. You would come out with some very clever ways of counting things. right? So very often that your tutor or me present a solution which divided into 5 cases, count each of them. But some of you may have a very clever way. Just look at this, done, right? So the combinatorics, the answer is never unique. The number in the end will be unique, but the method, different people can use different methods. As long as you have reasons, you are confident about what you are doing, you can do it in your own way. Okay, anyway, so I'm short of time, so let me just continue the examples. Okay, there are a few more examples on the circular arrangement. Okay, so let's look at them. So this is in general. In how many ways can you arrange n different objects in a circle, right? So this is a generalization of the 3 guests around the table. So you have n guests now. So if they were on the line, it would be n factorial, but we overcounted n times. Just now we overcounted 3 times. Now it's n times because you have one position. It's like a dial, right? So you click, 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 then you have n possible picks. Okay. Anyway, so the answer will be n minus 1 factorial. Okay. Now a few more. So now we still have a round table. There's 10 seats. It can hold 10 person. But we don't have 10 guests. We only have 9 guests. Okay, so let's see. So find the number of ways without removing any empty seat that 9 guests can be seated at a round table with exactly 10 seats. Okay. So the solution is, well, in this case, the empty seat can be treated as a different person, right? So it's still like arranging 10 person. Now, how about this? Wait, so is this okay? It's because if you don't only miss one person, but the seat has to be there, so you may imagine that's an empty guest or something. Okay. Now, how about 8 guests? The same conditions. You still have a round table with 10 seats, but this time you only have 8 guests. Well, now, this solution was too wordy, so okay, so let's follow it. So just imagine that in addition to the existing guests, we have 2 different ghosts, right, occupy the 2 seats. And then according to the formula, you get 9 factorials. But actually, the 2 empty seats are not different. It's not occupied by 2 different ghosts. They're occupied by, I don't know, the same ghost. Okay. So ghost 1 position here and there, actually they are the same. So somehow, because we treat the empty seats as different ghosts, we double count by factor of 2. So you divide by 2, so this is enough. Okay, I guess. Okay. So now, just now the counting involves orders. So you have clearly first position, second position, third position, so on and so forth. So now there is sometimes the order doesn't matter. You only want to collect people together and count, right? So the situation is many counting problems involve counting in the number of subsets of a finite set satisfying certain constraints. So the property of subsets is it doesn't depend on how you write them. The set bracket 1, 2 is the same as the set bracket 2, 1, right? So okay, so for example, let's try this. How many 5-person committees can be formed from a group of 8 persons? Okay. Now, okay. So given n different objects, how many ways can we choose k of them? Right. So these are the typical examples. Right. So the difference was in permutation, the order matters. So you have first position, second position. here, suppose you pick 5 person in the committee. You don't choose who is number 1, who is number 2. It's just 5-person committee. As long as the 5 person are in, they counted as 1. Okay, so now there's formulas. This number is more useful than, okay, this number C of nk is read as n choose k. Is more useful than P of nk, the permutation number. Okay, so first let me introduce this number. So let C bracket nk denote the number of ways of choosing k objects from a set of n different objects. Okay. Then the number is calculated in this way. Is n factorial divided by the k factorial times n minus k. Well, it's a mouthful to read this, but okay, so maybe I should skip the proof. I skip this proof because you can read it by yourself. So in the end, the conclusion is you can think of finding this number in this way. So first, you consider the order, right? You want to have a 5-person committee. So let's assume the 5 person actually has chair and so on. So then altogether, you have Pnk because this number consider the order, right? Now suddenly you say there's no order between the k people because you choose a 5 person in the committee. There's no position. So therefore, any combinations of within the committee doesn't matter, right? So how many ways of permute people in the committee? K factorial ways. So you divide by this. So this is the correct number. Well, the slides give you the reasons. Do the reasons in a very, very slow steps. Okay. So the answer is, okay, so this is the formula to compute this number. Okay, again, unfortunately, in literature, you have this for the same number. And more often you see this. It's like a small matrix. So it's a bracket, but with 2 numbers written in a column. The top is n, the bottom is k. Right? So it pronounced as n choose k for the obvious reason. It's a number where n objects you choose k of them. Okay. Then for the special case, you define in this way. This can be justified, right? Suppose I give you a number. I ask you to choose n of them. Then you don't have any choice. There's only one choice, right? So these are the obvious. Now, there are some properties. This n choose k is the same as n choose n minus k. To justify this is from n I choose k elements is the same as I leave out. I specify which objects I take. It's the same as I specify which object I reject, right? So n choose k is the same as it's n choose n minus k. It's like here I choose friends and enemies, right? So after I fix my friends, then the enemies is clear, right? Or it's the same. I choose my enemies and then the friends is clear. Okay. Anyway, so look at the example. So this is the committee. It's a slightly more complicated version than the choosing committee. Okay. So how many different 5-member subcommittees can be formed from a 9-member specified committee? Okay. If the president and vice president do not serve on the same subcommittee. Okay, read it one more time. So I have 9 members, right? Inside the 9 members, I have a president and vice president. So now I want to form a subcommittee, but subcommittee has 5 members. Okay. Right. So now I want to know how many different ways to form subcommittees. But there's a condition, there's a catch. I cannot put president and vice president in the same in the subcommittee. If I choose president, I cannot choose the vice president, and vice versa. Or I can reject two of them. Okay. Okay. So there are three ways. There are three types of subcommittees. So the type 1 is it contains president but not vice president. Right. So there are 7 choose 4 ways. You understand why this is 7 choose 4? Because why 7? Because I treat president and vice president differently, right? So they are outside my consideration. So in other words, the committee already have a position taken by the president, and then the vice president is irrelevant because he cannot be chosen. So therefore, to get the remaining members, I only have 7 people. Okay, so that's why it's 7. Now, among the 7 people, I only need 4 of them, so it's 7 choose 4. Okay, so by the same reason, if I choose, already determine I choose, I include the vice president, same number. Okay. Now, the last one is, it does not have both of them. Okay, so it's 7 choose 5. Okay, so altogether is this number. Right. Now we can calculate the typical example. Okay, so we have cars, right? So the total number of poker hands. Okay, so we have 52 cards. There's no jokers, I guess. So there's 52 cards. Now each time we choose 5. So total number. Okay, this number is irrelevant for the counting we are going to do this, we are going to do next. But next week we are going to talk about probability. So we need, this number is useful. This number is a total possibility. Okay, anyway, so the total number of possible poker hands are 52 choose 5. Okay, so it's some funny number. Now, how many ways to get this? To get this royal flush. Okay, so the royal flush must be 10, jack, queen, king, and ace. Okay, but there are only 4 suits, right? Diamond, spade, and so on. So there are 4 ways. There are only 4 ways. Okay. Now, how about these? Suppose you don't need to start from 10 all the way up. You can just, as long as they come from the same suite and consecutively. So how many of them? Okay, so let's try. So there are 4 suites, right? So again, club, diamond, heart, and spade. So there are 4 suites. For each suite, you have 9 straight flashes. So because you start from 1 and with 9. Sorry. You look at the 5 cards, right? You look at it was determined by the smallest number. Because once you choose the smallest number, the rest have no choice. Because, for example, if your smallest number is 5, the next one has to be 6. Right? So how many straight flush is determined by how many ways to choose the smallest number. So the smallest number can start from ace and with 9, because if it's 10, it belongs to the first category. So there's 9 choices. So it's 4 times 9. Try again. I can form this hand by 2 steps. First step, choose suites. The second step, choose the smallest number. Okay, how many ways to choose suites? 4. How many ways to choose the smallest number? Okay. It should be 10, but if I choose 10, I'm here. So this the second case exclude the first case. You don't want to have overlaps. So this is exclude royal flash. Right? So therefore, you only have 9 choices. So it's 4 times 9, 36. Okay, so then we count a few more, and then the remaining ones will be left as homework. Okay, so now we want to have four of a kind. In other words, among the 5 cards, 4 of them are the same. Okay, so now let's okay, so again, imagine that we form this hand in 2 steps. The first step is to choose the 4 cards of a kind. The second step is to fill out the remaining one. Okay. So how many ways to choose the same card? Well, there are only 13 choices, right? From ace to king. So there are 13. So after determining the 13, you have to choose one more card, right? So after you get this, so there are 48 cards left. You choose any of them. So therefore, the total number is this: 13 times 48. Okay, so then it's what? So this is a full house. Okay. So the full house are you have 3 cards of the same number, and then the pair also same number. Okay. So so we want to count how many. Okay, again, imagine we get this hand in 2 steps. First, choose the 3 cards, and then you choose the pair. Okay. So how many ways to choose the 3 card, the 3 cards of the same number? So the number will be 13 choices. Right, because there's 13. And then you have to okay, suppose you choose 8. There are 4 8, but you only choose 3. So you have to decide which 3. Or equivalently, you have to decide which one you throw out. Right? So therefore, to choose these 3 cards, you have 13 times 4 choose 3, which is the same as 4 choose 1. So you have these choices for the 3 cards. Now for the pair, now you originally you have 13 cards, but once you choose the 8 is out. So you have 12. So you have 12 numbers to choose. Now once you choose a number, say let's say is a king. And then among the 4 kings you have to choose 2 of them. So you have a 4 choose 2. Right? So there are this many ways of finding the pair. So altogether is you multiply, right? This is multiplication principle. You do it. Okay, so this is the way. And okay, so so let's count this. This is called flash. So it's but we don't want to have the royal and straight. So the thing we have counted, we don't want to include, right? So they are from the same suites, but they cannot be consecutive. Okay. So so this time we can. Okay, we use a different method. Usually we say how many ways of doing this, how many ways of doing that. Now this time is too troublesome. So let's do a different way. So there are 4 suites, right? So you choose the suites first. Now for each suites, there are 13 choose 5 ways of picking 5 cards. But among the 13 choose 5, you include the 2 cases we have considered. So you have to minus them. So you have to minus them, that's, I don't know, it's 10 of them, right? Each of so after that, after you subtract away those you have considered, you get these. Okay, is it? Okay, so there are a few more. Okay. Okay, good. So I still have some minutes. Okay, so let's try this. So now we try to count straights, right? Again, we have to exclude the thing we have counted. So these cars are so they are consecutive. They form by the 5 consecutive numbers, but not from the same suite. Right? Okay. So there are 10 choices for the lowest number in a string, right? So from a's to 10, there are 10 choices, and for each, after you determine the number, you have the freedom to choose the suites, right? So there are 4 of them. So altogether is 10 times 4 to the 5. But among these, you include the thing we want to exclude. So you have to minus them away, right? So before that, I think the total number of these 2 cases are 40. So you take away 40, you get 40%. Okay, 3 of kind. Okay, so 3 of kind by definition is you have, okay, it's like the 3-8 here, but the remaining 2 cards cannot form a pair. If you form pair, it's called a different name, right? So it's 3 of kind, but the other 2 are different. Okay, so let's see how to. So again, there are 13 choices of the number in the triplet. For example, the 8 here. And this is exactly the same as the full house. Right? So for a given number, there are 4 to 3 of the suits. Right? So that determines the triplets. Now we need to pick 2 cards from the remaining 48. But we have to ensure that they have different numbers. Right? So the number of ways is, okay, so okay. For the second step, I claim the total number is 48 times 44 divided by 2. Okay. So sorry. So this 13 times 4 comes from this paragraph. You have 13 here, you have 4 here. So 13 times 4, not determining the triplets. Now I want to convince you the number of choices of these 2 cards is this. Okay? So why? So first you can choose, is it right? Yes. Okay. So the 48 is because although you choose 3 cards here, the last card you cannot use. Right? So you only have 48 choices. Now once you choose the first one, for example, you choose a 10, then you cannot choose another 10. So therefore you exclude 4 cards. Although you choose 1 card, the other 3 you cannot use. So you exclude 4 cards. So therefore, when you draw the second card, you have 44. Okay. Now why divided by 2? Because when I consider 48 first, 44 second, I could have 10 and 8. Right? I could also have 8 and 10. Sorry. Suppose I don't divide by 2, right? So my counting include this situation, I first draw a 10, which is the 48, choose 10. Then I draw an ace, that's the choice from 44. So this I already count. So this is one choice. But inside this 48 times 44, it also includes, I first draw ace, because ace is also the 44, so 48. So it include, I first draw the ace, then draw the 10. So therefore the pair, I count as 2, but in my hand they are the same. So I have to divide by 2. You may have other ways of doing counting. So you may have some different expression. I don't know how you do it. So, but this is one way. Okay. So there are other cases. So in the tutorial, you are going to discuss this. It's fun, right? Do I have time? So maybe I'll go through the binomial theorem, and then the next item I'll leave it next week. Okay, so now the binomial theorem starts from expanding the power of this form. Okay, because I believe you have seen this, so that's why I want to rush through this. Okay, so the number n choose k, also called binomial coefficients, it comes from this so-called binomial expansion of this power, a plus b to the power of n. These things I'm sure you learned in JC, how to evaluate a plus b bracket square. So this is a square plus 2ab plus b square. And then by hand or by MATLAB or whatever, you can evaluate the rest. So the a plus b to the power 3 is this. Okay, I don't read. So but the coefficient is 1, 3, 3, 1. The next one, the coefficient is 1, 4, 6, 6. Okay? There's something wrong. There's a this is 4. Sorry. Okay, I'll correct it. So there's a mistake here. Okay. So in general, you can express the power a plus b to the power of n in this funny sum, right? It's a sum of lots of terms, but the point here is the terms are actually those n choose k. So the terms are, that's why it's called binomial coefficients, right? So if you expand a plus b to the power of n, you get a sum, okay, for example, the sum, where you start from the highest power of a, and then drop the power of a by 1, increase b by 1, right? You start from the highest power, which is 3, and then you drop a by 1, you get square, and b increase 1. Then you drop a by 1, increase b by 1. So you have all these, right? So in this expression, the total sum of the power is always n, right? So this is n plus 0. This is n minus 1 plus 1, which is also n. This is n plus 2 plus 2 is n, right? But the coefficients are those n choose k. So n choose 0, n choose 1, n choose 2, and so on. So this is this equation is called binomial theorem. So there's a proof. Say, how do I get why there's n choose something? So the reason is, how can I get? Okay, I think you believe me that every term, if you expand, every term must have this. Okay, the power must have this form. You have bunch of a, you have bunch of b, but the total number of a, b must be n, right? Because this is a n-fold product. Each one you choose one number, so the total number has to be n. Right? It depends on how many a's and how many b's. Okay, so definitely any term must be some a's and some b's. So let's assume the term are like this: a n minus k times b to the k, or some k. Okay, how many ways I can get this term? Well, this is a product of So this a plus b to the power of n, this is a plus b, dot dot dot, a plus b, right? N copies of a plus b. Now suppose I want to get this, my favorite term, a to the some power and b to the, let's say b to the k. It's easy to read, b to the k. Suppose in the product here, I want to get b to the k. How do I get b to the k? So I must choose k many b's from the brackets. Right? So among here, I have 1 copy, 2 copies, 3 copies, or have n copies of a plus b. Now to get b to the k, I must choose, we must choose k copy of b in the bracket. Maybe this one I choose, this one. So among the n brackets, to form this b to the power of k, I have to choose k of them. So that's why I have this n choose k. I don't need that. Okay, so that's the reasoning. So I will not go through basically this paragraph just saying that. Okay. So now this there's an easy way to remember the coefficients. So it's called Pascal triangle. In Chinese they call it different name. There's a Chinese mathematician. Okay, so let's say the third row corresponding to a plus b squared. So you get a squared plus 2ab plus b squared, right? Then this is a cubed plus 3a squared b plus 3b squared a plus b cubed. So each time so these things are the binomial coefficients. So what is an easy way? You can calculate this 6, for example. It's a sum of the 3 and 3. Look at this 21. 21 is a sum of 15 plus 6. So to form the triangle, there's a pattern. You draw ones on the side, and then in the middle, you just add the 2 neighbors on top of you. So this is a way to form the triangle. So this was known to Pascal and so on and so forth. Okay, so okay, so I will stop after reading this. Next time we do this. Okay, so from this triangle, we observe that this number comes from the 2 neighbors on top of him. But this number has an expression. This number, for example, this is n plus 1's row. So this is n plus 1 choose k. Now, his 2 neighbors are these. So if he is from, suppose, imagine this is n plus 1 row, right? This is the k's position, right? So we said this number comes from the 10 and the 5, which is this and that. Okay? Now his position is n plus 1 choose k. Right? Now who are these guys? So certainly if 15 is on the n plus 1 row, this is the nth row. Right? So certainly they are n choose something. Right? Now what are the things they choose? So 15 is the k's position. So actually the 5 is the k's position. The 10 is k minus 1, is the guy before k's position. So we have this equation. From the pattern, we observe that the pattern actually tells us the binomial coefficients has this property. The n plus 1 choose k actually is the sum of the 2 numbers, n choose k plus n choose k minus 1. Okay. So next time we'll show this. We'll give maybe 2 different proofs, and Then we continue some counting. Okay. Sorry, I ran over time. So see you next week. Next week we'll continue from this.